Okay, it is time for tricks of the trade. Today we are going to talk about something called logarithmic differentiation. Differentiation. Hard to say and write at the same time, but we've got problems where we have powers of x in both the base and the exponent. Can't use a power rule because power rule only works for x to the power of some real number. Can't just use that as chain rule because, well, this isn't e to the x or a to the x. So exponential doesn't work, power rule doesn't work. So what we're going to do is logarithmic differentiation says that if I have y equals some function to the power of some other function, if I take the log of both sides, I can use implicit, well, first of all, I can rewrite this as natural log of y equals g of x times natural log of f of x. And I can use implicit differentiation on this side, and I can use the product rule on this side. So let's do that with y equals x to the x. I've got the natural log of y equals x times the natural log of x. The derivative of natural log of y is 1 over y times the derivative of y. This is a product. We'll call this u. We'll call this v. So u dv plus v du. Doing some simplification, I get that y prime equals y times 1 plus natural log of x. And of course, y is equal to x to the power of x. So the derivative of this function is x to the power of x times 1 plus natural log of x. Pretty straightforward, really. The trick is just keeping track of everything because you've just got a lot of things going on here with your implicit differentiation and your product rule. So let's do a quick example. We've got a flu spread. Well, this doesn't actually have anything to do with logarithmic differentiation. No, it sure doesn't. Okay, well, we're going to do an application. Wait, stop, go away. We're going to do an application example of all this differentiation. It is not an example of logarithmic differentiation. We've got a function that models the spread of a flu virus. Yeah, if you're watching this in 2021, maybe thinking, yep, been there, done that. And we've got a variety of questions regarding this virus. P of t is the number of infected students since the virus was noticed. So the students could have gotten better. It's just a total. And t is, of course, days since identification of the virus. Identification, when they realized identification that there was a virus spreading. So A, initial number of students infected. Well, of course, that means what happens at time 0. P of 0 equals 100 over 1 plus e cubed. And if you type that into your calculator and round it to the nearest whole number, you get 5 students. Question B is the rate of spread after 3 days. Well, of course, rate is p prime, and so we're looking for p prime of 3. So let's find that derivative. We had that the function was 100 over 1 plus e to the 3 minus t. general rule, taking the derivative, you have a function in the denominator, make it a -1 power. So the derivative equals, well, 100 times, that's the constant, power rule, -1 times that to the -2 times the derivative of the inside, well, the derivative of e is itself, times the derivative of the power, -1. So what I get is I get 100 e to the 3 minus t, all divided by 1 plus e to the 3 minus t squared. Notice that the negatives have canceled each other out. And setting times 3, well, 3 minus t is 0, so e to the 0 is 1. 1 plus 1 on the denominator is 2. 2 squared is 4, which means that this is spreading on day 3 at a rate of 25 students per day. So let's talk about the next question is, when is the maximum rate of change of the spread of the virus? Well, if I look at the graph of P prime, what I see is that it looks something like this, and that maximum appears to be about day 3. What's the official way to do this? Well, a maximum is going to be the place where there is a tangent line with a slope equal to 0. So really my official answer is that P prime of t equals 100 e to the 3 minus t over 1 plus e to the 3 minus t squared. I could do a quotient rule problem, and I could find the second derivative, and I could set it equal to 0. I'm not gonna. It's a long, complicated problem. It wouldn't be the end of the world, but I don't really want to do all that algebra right now, and we don't really need to, because looking at the graph of P prime, and by the way, we're going to get back to this in some later, actually next chapter, so this is really a setup for the next chapter. But what we do notice, what we want to take away from here, is that the tangent line has to have a slope of 0 if we're at an extreme value, a maximum. All right, so those of you in my class, go ahead and do exercise 51. And I'm going to include the recap in this video, so I'll pause for a second, or you can pause. All right, let's do a quick chapter recap or section recap of 4.4 because it's quick. What did we figure out in this chapter? Well, we figured out the derivatives of e to the x, a to the x, natural log of x, and log base a of x. We figured out that the derivative of e to the x was itself, that the derivative of a to the x was itself times the natural log of a, that the derivative of natural log of x was 1 over x, and that the derivative of log base a of x was 1 over natural log of a times 1 over x. We talked about logarithmic differentiation. And the basic differentiation, oh my gosh. Just talking and writing complicated words. Differentiation. If I've got y equals f of x to the g of x, I take the natural log of y. I take the natural log of both sides. I do a little fiddling algebraically, and then I use implicit differentiation on this side, and I use the product rule on this side. And don't forget to use the chain rule for natural log of f of x. And we could actually come up with a formula for this very simply. It would be 1 over y times y prime is equal to, well, u dv, which would be 1 over f of x times f prime of x plus v, natural log of f of x, du g prime of x. And then, of course, don't forget to multiply both sides by y, which is f of x to the power of g of x. So you want to always solve this for. But I don't think it's worth memorizing that formula. The key here is really that logarithmic differentiation. It applies to function raised to the power of a function, and we just take the natural log of both sides. What do you need to know? You should know those 4 derivatives. You should recognize when to use logarithmic differentiation, and then the fact that you need to do implicit and product rule. That's everything from section or chapter 4.4 of our book. We will see you back here for chapter 5 when we'll start talking about finding minima and maxima for functions. All right. Hey, thanks for watching. I hope you learned something.